Hello everyone. In today's session, we will learn about deep neural networks. Deep neural networks are one of the most powerful techniques in artificial intelligence and deep learning. They are capable of learning highly complex patterns from large amounts of data and are widely used in image recognition, speech recognition, natural language processing, medical diagnosis, and autonomous vehicles. In this presentation, we will understand the architecture of deep neural networks, learn about weights and biases, study different layers, explore activation functions, and finally, discuss optimization algorithms that help train deep learning models efficiently. Let us first understand what a deep neural network is. A deep neural network is an artificial neural network that contains multiple hidden layers between the input layer and the output layer. A network is generally called deep when it has two or more hidden layers. Each neuron in the network performs four basic operations. First, it receives input values from the previous layer. Second, it multiplies each input by its corresponding weight and calculates the weighted sum. Third, it applies an activation function to introduce non-linearity. Finally, it passes the output to the next layer. As information moves through successive hidden layers, the network learns increasingly complex features. Say, for example, in image recognition, the first hidden layer may detect edges, the next layer identifies shapes, and deeper layers recognize complete objects such as faces or cars. Now, let us understand the parameters of a neural network. The two main parameters are weights and bias. Weights determine the importance of each input feature. A larger weight means that the corresponding input has a stronger influence on the final prediction. During training, these weights are continuously updated using optimization algorithms such as SGD or ADAM. The second parameter is the bias. Bias is an additional value added to the weighted sum before applying the activation function. It allows the neuron to shift the activation function and improves the flexibility of the model. The mathematical expression shown on the slide represents the process. First, the weighted sum is calculated as Z equal to Wx plus B. Then the activation function transforms this value into the final output represented as Y equal to F of Z. Every deep neural network consists of three types of layers. The first is the input layer. This layer receives the input features from the dataset, such as image pixels, sensor readings, or patient information. The input layer only accepts data, it does not perform any computation. The second is the hidden layer. These layers perform the actual computation. Each hidden layer applies weights, biases, and activation functions to extract meaningful features from the input. A deep neural network always contains two or more hidden layers. The final layer is the output layer. This layer produces the final prediction. The number of neurons in the output layer depends on the task. For binary classification, only one neuron is required. For multi-class classification, multiple output neurons are used. For regression problems, a single neuron predicts a continuous numerical value. Activation functions are one of the most important concepts of deep learning. An activation function determines whether a neuron should be activated or not. More importantly, activation function introduce non-linearity into the network. Without activation function, every layer would simply perform linear calculations and even a very deep network would behave like a simple linear model. Activation functions enable neural networks to learn complex relationships, improve prediction accuracy, and solve real-world problems such as image classification, speech recognition, and language translation. Let us first study two traditional activation functions. The first is the sigmoid function. Its output ranges from 0 to 1, making it suitable for binary classification problems where predictions represent probabilities. Its main advantage are its smooth curve and probabilistic interpretation. However, sigmoid suffers from the vanishing gradient problem, which slows down learning in deep networks. The second activation function is tanh or hyperbolic tangent. Its output ranges from -1 to +1. Because it is a zero-centered, tanh generally performs better than sigmoid. However, tanh also suffers from the vanishing gradient problem when networks become very deep. To overcome the limitation of sigmoid and tanh, the ReLU or rectified linear unit was introduced. ReLU outputs 0 for negative values and returns the input value for positive values. It is computationally simple, trains much faster, and significantly reduces the vanishing gradient problem. For these reasons, ReLU is the most commonly used activation function in hidden layers. However, ReLU has one limitation called the dead neuron problem. If a neuron's input remains negative for a long time, it may stop learning completely. To solve this issue, leaky ReLU was developed. Instead of outputting 0 for negative values, leaky ReLU allows a very small negative slope. This small modification keeps neurons active during training and improves learning performance. Another important activation function is a softmax. Softmax is mainly used in the output layer of multi-class classification problems. Instead of producing a single value, softmax converts the outputs into probabilities. The probabilities of all classes always add up to 1. The table on this slide compares all major activation functions. Sigmoid is suitable for binary classification. Tanh is mainly used in hidden layers, although it has a less frequently today. ReLU is the most popular activation function for hidden layers because of its speed and effectiveness. Leaky ReLU improves upon ReLU by preventing dead neurons. Finally, softmax is the preferred choice for multi-class classification problem. Once the network makes predictions, it needs to improve its accuracy. This is achieved using optimization algorithms. The objective of an optimizer is to minimize the loss function by updating the weights and biases. The optimization process begins by initializing the weights. The network then performs forward propagation to generate predictions. The loss is calculated by comparing predictions with the actual outputs. Next, propag- proba- backpropagation computes the gradients. Finally, the optimizer updates the weights using the gradient descent formula shown on the slide. This entire process repeats until the loss becomes sufficiently small. There are three common approaches to gradient descent. The first is batch gradient descent, where the optimizers process the entire dataset before updating the weights. It produces accurate gradients but requires high memory and takes longer to train. The second is stochastic gradient descent or SGD. Here the optimizer updates the weights after processing only one training sample. This method is much faster but produces noisy update. The third is mini batch gradient descent. Instead of using the whole dataset or a single sample, it processes a small batch of data such as 32, 64, or 128 samples. Mini batch gradient descent provides an excellent balance between speed, memory usage, and stability, making it the most widely used optimization technique in deep learning. Several advanced optimization algorithms have been developed to improve gradient descent. The first is momentum. Momentum remembers previous gradients and helps the optimizer move more smoothly toward the minimum, reducing unnecessary oscillations. The second is RMS prop. RMS prop automatically adjusts the learning rate for each parameter using the history of squared gradients. It performs particularly well for recurrent neural networks and non-stationary problems. The third and most popular optimizer is ADAM, which stands for Adaptive Moment Estimation. ADAM combines the advantages of both momentum and RMS prop. It provides adaptive learning rates, convergence quickly, and is robust across many deep learning applications. For these reasons, ADAM is one of the most widely used optimization algorithms today. This slide compares the major optimization algorithms. Batch gradient descent is a slow and memory intensive but provides stable convergence, making it suitable for small datasets. Stochastic gradient descent is much faster and requires less memory, making it useful for large dataset. Mini batch gradient descent combines speed with stability and is the standard choice for most deep learning models. Momentum improves convergence by reducing oscillations. RMS prop adapts learning rate and is especially useful for sequence models such as recurrent neural networks. Finally, ADAM combines momentum and RMS prop, providing fast convergence, adaptive learning rates, and excellent performance across CNN, RNN, and transformer models. Because of these advantages, ADAM is the optimizer most commonly used in modern deep learning. Let us summarize today's sessions. Deep neural networks contain multiple hidden layers that enable them to learn complex patterns. The two learnable parameters are weights and bias, which are updated through backpropagation. Activation functions introduce non-linearity, allowing neural network to solve complex real-world problems. Finally, optimization algorithms such as ADAM efficiently train deep learning models by minimizing the loss function. Together, these functions form the foundation of modern deep learning. That's all about today's session. Thank you.